Okay, well, does everyone remember linear algebra? What's the take home from linear algebra? Larry? Well, that's the take home from my take. Okay. Uh, I wish that I could make a whirlwind tour of all linear algebra classrooms and try out that theory. That's what linear algebra is. But you know, I think for 99.99% of people, linear algebra is it's a phrase that has two words, both begin with R. Yeah, I think matrices are row reduction, of course, column reduction too, row and column reduction. Okay, that's 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 what. And to be honest, that's what I would, if I wanted to prove any of these trivially equivalent theorems, I would probably start with row reduction because they're tricky proofs, but I never can remember them. Okay, I mean, I've studied them, and there are lots of interesting proofs of the non-trivial theorems. So definitely, I'm not ashamed to say that this linear algebra is the mainstay of this course, and the case theory is based on linear algebra. The fact that, and that's so one of these trivially equivalent non-trivial theorems. K0 of the field is what? Right? Okay, have you checked that? Good. Okay. Okay. Well, let's see what let's put it into practice. Let's see if it works. So the idea was we have a C-star algebra A with units, or Banach algebra, complex Banach algebra, and C-star algebra if you want, but you can't ignore the fact that it's a Banach algebra for the proof in the book. Okay, so we look at K0 of A, and it was the K1 of S of A. K1 defined in terms of vertical elements, okay, or it's the C-star algebra unitary element, but it's the variable elements modulo connected components of the unit. And if you don't have a unit, you join a unit. And for the complex numbers, you don't have to worry about throwing it away. You don't have to worry about recycling the unit. And you go to matrices too. You have to do the same thing for matrices. So we have we want to prove surjectivity. What was our strategy? We have the maps and the groups. So first of all, the maps. Well, if we want to get a group map, we get the surjective index. This is what the injectivity is a consequence of the surjectivity. You do it for instead of the original algebra, you look at continuous functions and code into the interval, into the surjectivity. Okay, so we have we want to prove subjectivity. Yeah. So we suppose we have a map from the suspension is continuous functions on the circle that are scalar multiple of the unit. So that's a special point one on the circle. So maps into A. Maps into A. So one. Well, either the scalars being scalar multiples of the unit, or if we were looking at matrices, then we're going to have to deform into matrices, but also at the beginning we have to look at matrices too. So that's not what we do. So I got a better piece of software. Much easier to read. I can read it more easily. Okay, and so this curve F, we want to want the homotropic to a very special kind of curve, right, inside matrices. So, but it should be homotrope to some projection, some idempotent T times Z plus some 1 minus T, where 1 is the unit in some n by n matrix. And the first step was to pass to the case with using the Barth-Cluster and the fact that on a compact outsource space you have a partition of unity, or a partition of unity that's sitting inside, well, say subordinate to given open covering, open covering space. That's how you reduce the polynomial case. So, yeah. This is sort of before we get to the row reduction, we reduce pre-reduce. That's the A0 plus A1 plus A1 to the end. Except you have to start off, if you look at the approximation term, in terms of trigonometric polynomials, we discussed that. So if we want an ordinary polynomial, it's a approximation degree, so we multiply through by power of Z to get rid of the term. And since the as I discussed before, we're using that this is a group, that the image is a group. We're given an element of the image, that we're allowed to prove that it is in the image. We're given an element of the codomain. Prove it's in the image, we can multiply it by something that is in the image, or add it to something. In fact, in terms of the group operation, we can modify it by something that is in the group, and sufficient to prove that the resulting element is the group. That's how we convert a trigonometric polynomial, or a raw polynomial, into ordinary polynomial. Okay. This now is still one-by-one matrices. If we start out, if the loop, the continuous path is one-by-one matrices, where the coefficients of the polynomial. And the whole curve is in so what that says, by the way, is that 0 plus 1 plus 4 is some scalar invertible matrix, so we can multiply. We can take the curve constant equal to that. That would be a trivial curve, and we can multiply by the inverse of that. Of course, it's exactly convenient. Of course, by 1, you mean this stage, it's still the unit of A, or the matrix algebra over A for given curve fit. Okay, so it's 1 by 1 matrices, but we know before we discuss what the main strategy is. It's row reduction, right? So you got to have a matrix from the row reduction. Now, it's true your given path might be in a matrix algebra, but it might not be. It might be just the algebra itself, or then 1 by 1 matrix. So in the textbook, Professor Rordam and his two that time students do a very careful calculation of the exact size of matrices that's needed to get rid of the higher powers of the Z. Okay? We're never going to get rid of Z to the first, because we don't expect to have a constant curve. We don't expect to end up with a constant curve. But a linear curve will have all the properties that we right? This and this is an optimal result, and that's reducing the degree by 1 requires going. Well, reducing the degree by n minus 1 requires going to n minus 1 by n minus 1 matrices. Someone can check that that's what the formula in the book gives you. Okay. Has anyone checked it already? Okay. Well, it's you just have to glance and see how large the matrix is. I think they even write the matrix out. So it's polynomial linear. But let's not try to get an optimal size of matrices. Let's just double the size, the given size, until we can reduce the degree by 1. So instead of instead of n minus 1, we're going to get 2 to the n minus 1, 2 to the n minus 1 matrix. I don't think, given we have to go to matrices, I don't think anyone is going to mind too much how large the matrices are. Well, that's sort of a second or third order subtlety. Okay, so let's look at the simplest way to introduce 2 by 2 matrices. We just look at Z, the upper left-hand corner. The diagonal matrix with 1 and the other diagonal division. 0 off the diagonal. Okay. This is the path with invertible elements of 2 by 2 algebra, 2 by 2 matrix algebra over the unitization of A. In other words, 2 by 2 matrix valued functions on A, which are 2 by 2 matrix value functions on the circle with the special point 1 are, in fact, this one is equal to the identity matrix as point 1. Okay, so I'm open for instructions. What should our next, what should our first row reduction step be? Abigail? Well, okay. Well, okay, by the way, we're not going to try to get rid of, no, right, exactly. The trouble is if we and then you're saying maybe put it up here after I, okay. But the trouble is, if we do that, in the next stage, if we move it over, we're going to be stuck with the Z to the nth here, and we will get rid of this one, and we'll still have this one. So, but why not be a little less ambitious and just aim for Z? Try to get rid of Z. So why not so put the same thing and up here, why not just put or because then the next time we can multiply by Z to the n minus 1, and then we're never going to get any terms of there won't be any residual terms of degree n. Okay, so let's try it with Z. By the way, it would be why don't we be a little more sort of preparing for the future? Why don't we put an AN here too? So the next time we just have to multiply by Z to the n minus 1. And then this matrix is the value. AN doesn't belong to AN is just an element of the algebra. It's not a scalar. But when Z is equal to 1, we want the whole thing to be a scalar matrix. Right? So this could be a 1, we'll have a 1 here. We'll have the unit element here. So this. Z is equal to 1, this is AN. So why don't we subtract AN? Subtract AN. Then when Z is equal to 1, this is 0. And it's, in fact, it's even the identity, it's even the unit element, okay? Which is sort of that's sort of an ideal behavior. For this final step, it's going to be quite handy to have the final curve, final linear curve. General linear curve down to 0 plus A1Z. But this doesn't mean that A1 is an idempotent, okay? So, okay, but then at the next stage, we keep the next stage. We have the same thing here, the same thing here. But it won't be the same thing here anymore because we're moving things. We're doing column reduction, right? So we multiply this column by something and subtract from the first column. And, but then since this is a 1 down here, whatever we multiply, what we choose what we want to multiply by looking at this upper right entry. but we have to then remember that it hits the lower right entry too, and so we'll get. So what is it we should multiply by? Okay, let's try that. Who said that? Yeah. Oh, okay, good. How many people agree? Okay. Well, okay. I mean, we're you're not putting you're not Rishi is the only one that's putting money on it. Okay, so and what do we have here? Well, we have star, and then I guess we want to subtract, okay? Because we could have put a minus sign here, but the way it is, as long as we keep track. Okay, but then that means that what we have here is after we've taken the z to the n minus 1 times this, so that gets rid completely of the z to the nth term. And so what it, on the other hand, the z to the n minus 1 term is going to be an times z to the n minus 1. Oh, there's also an plus an minus 1, which is still there, plus an minus 1 plus an. Times z to the minus 1. Well, notice that this is really quite fun. We wanted things to be just equal to the unit at the sector point 1 on the circle, right? Well, it seems to me that that's what's happening. We put z equals 1, so we still have the sum of all the ans, so that's 1. Okay. So, oh, we have a 1 here. Well, okay, but that doesn't matter because that's at least it's a complex number. So we have this final matrix, which is now of degree n minus 1. Polynomial coefficients are, well, the coefficients are in 2 by 2 matrices over A, except the when evaluate that z equals 1, sector point 1 on the circle, we get a scalar matrix. All 3 of the terms are scalars. This one is still 0. The upper right is still 0. Lower left is 1. They're all 1 except the 2 ones down the diagonal and 0 upper right and then 1 lower left. Well, we can just multiply. That's a scalar matrix, invertible. We just multiply to look at the constant curve equal to that matrix multiplied by the inverse, and we have something that's equal to the unit everywhere. Sorry, it belongs to 2 by 2 matrices of A everywhere, and it's of course the scalar matrices are an exact component. It doesn't deformation of the original curve. And we now have the unit matrix. Okay, so that's the. We can do it once. We can do it any number of times. Right? Yes, we could. What is it we did multiply? We multiplied by minus z to the n minus 1. Or we multiplied by z to the n minus 1 and subtracted. But what are you suggesting? Add 1 here. So you're saying multiply. Okay, well now we've got to multiply two things that are not monomials, right? Can you do? You've done that? Yeah. Well, okay. That's neat, yeah. And so let's multiply this by what we multiply. We want to multiply. We're subtracting. So multiply it by z to the n minus one minus one. And you're saying that that's equal to one. Oh, no. By the way, when we do the row reduction, this doesn't change. Sorry, if we do a column reduction on acting on this column, then the when we're finished, the other column gets changed, but this one is the same. So, oh, but okay, but if you did multiply by z to the n minus one, the question is whether does it still give you one here when z equals one? Okay, well that's quite. I'd say that's quite tricky, and I mean, that's very nice if it works. So why don't we leave that for people to check if they wish? Okay. In the repeat maybe is ahead of the game, but if you would like to have it, this would be a little more direct than the sort of hindsight thinking that you have something offside, a scalar value matrix convertible, and you sort of unpeel it. That would work. It's nice to get exactly on the button the first time. Okay, but let's take a look at what we if it is a linear polynomial. It could happen. Very unlikely, I guess, that the shown Weierstrass approximation, which is using the position of unity, subordinate to a fine covering of the space by open depth, covering of the interval of the circle by small intervals. The original polynomial after you multiply through. So if you're going to get it's going to be a linear polynomial, that means that before you multiply through by a power of z from the Laurent polynomial, it's going to be a polynomial in negative degree. Well, actually, and it can't be and it must be just negative degree 1. Okay. And so, but in that case, you might just as well, if it's already there are no positive moments, you might just as well work with the negative one. That's a perfectly good degree, degree. Okay, so we don't really have to. Multiplying by a power of z at the beginning is unnecessary if the well, in certain cases, but one way or the other, there's a lot of either sort of given laid out on a plate, or work for really hard the row reduction, the row and column reduction. That was hard work, right? Not just 10 years ago, or less than that for you and more than that for me, right? But it was a hard work then, and it's hard work now. We're not finished because we're perfectionists. We want to have the most elegant approach. The one that we want to go to a lot of trouble to save a little trouble. This is a worthy endeavor, I guess. Sure, no, definitely. Okay. So So what do we do if it's a linear polynomial? And clearly that's what we're looking for. Because I mean, the forward maps work with linear polynomials, and so the implication is that with the homotopy classes of these things in matrix algebra, maybe we'll exhaust arbitrary linear curves of the homotopy. Curves that still make these. Okay, but okay, so what do we do? By the way, let's just make a rough plan for next week, which is the last week of term. And there's Monday and there's Wednesday. And then there's Makeup Monday, kind of a hypothetical Monday, visionary Monday. It happens to be, this year happens to be on a Thursday. It'd be very confusing. Wouldn't it be confusing if Makeup Monday were on a Monday? I suppose the Monday part of it, the Monday sort of part of the name, because Thanksgiving is on a Monday. I don't know anyone that has the Thanksgiving dinner on Thanksgiving. So I did suggest that if someone wanted to discuss the proof of the spectral theorem, they could do that on the Thursday. Number of proofs. Maybe everyone could come with their favorite proof. Theorem for either for a self-adjoint operator, Hilbert space, complex space, or for a normal operator, or unitary operator, normal operator. That has to be a complex one, or fraternity on it. I suppose it would work on fraternity on it too. The self-adjoint one works in the real number. Some proof works well independently of what the scalars are, without even using the fundamental theorem of algebra. Those complex numbers. Right, it's not called the fundamental theorem of complex analysis. So complex analysis, that's what we're coming to. We're working over the complex scalars now. And, we're going to use that. Don't forget, the theorem isn't even true over the real scalars, right? And this map makes everything we've done so far. It doesn't use complex scalars. And I don't think it's the injectivity alone that depends on the complex numbers. I think it's the surjectivity as well. Well, the injectivity for the complex numbers, we have a curve of matrices over the complex numbers. Get that it improves injectivity for that's such a thing, that it starts off as say Z on the Z111 on the diagonal. Sorry, that's start off homotopy for that. We want to know, well, so it can't be homotopy just to the identity. We're going to make so that's injectivity. That's kind of injectivity, the specification injectivity. proof of that is you take the determinant of the matrices, and that brings it back to one by one matrices, and that's elementary theory, very elementary theory as well. One number is in the property invariant. So, how many people have studied complex analysis? Good. Well, good for the ones that have. That this is something called the holomorphic functional calculus. Just like the special theorem is the continuous functional calculus. You know, the self-adjoint operator on a Hilbert space. You have a continuous real or complex value function. Well, it's defined on the real line thing. It's continuous. And the plug in a self-adjoint element, and that's continuous functions that continuous in the continuous function. If you move the continuous functions continuously in the soup norm, then the operator you get by plugging in the self-adjoint element moves continuously. And if you have a polynomial, or if you plug the operator into a polynomial, you don't need the self-adjoint. If it is self-adjoint, then the construction agrees with what you get just looking at the polynomial and a continuous function. Okay, so that's continuous functional calculus. Self-adjoint element. So, and it's enough. The functions are continuous, not on the whole line. They just have to be continuous. If operators of norm 1, then you look at the interval from -1 to 1. If the function is continuous there, then business. Well, if it's not a normal operator, then you can still apply functional calculus. You can apply a polynomial. You can always substitute anything into a polynomial as long as you can add and multiply. Any algebra, a polynomial with coefficients in the field, you can plug in the elements of the algebra into the polynomial. It's a complex. If the field is a complex number, and we're talking about a bounded operator. The Hilbert space, the Banach space, or just an element of the Banach algebra. But then the by the way, for the self-adjoint element, you don't just have to. If it's operators of norm 1, the function doesn't have to be continuous on the interval from minus the norm of the element to the norm of the element. It's enough that it be continuous on the spectrum of this given self-adjoint element, okay? So the continuous functional calculus is for continuous functions on the spectrum of the self-adjoint element. The subset of the complex plane. The self-adjoint subset of the real number. Well, why am I saying that? Well, I'm saying that because in the present setting, we want to work with holomorphic functions, functions that are holomorphic. So it might be that the element has a certain norm, and in that case, looking at a disk in the complex plane with radius, the norm of the element. If the element is norm 1, then you might look at functions. Well, it's true if you have functions that are holomorphic from some open set strictly containing the unit disk. And then you can plug in your elements. You can plug in the element of any complex Banach algebra. And by the way, this construction has the same properties. If it's a polynomial, then it's obvious what you get. It's consistent. And a bunch of holomorphic functions will converge converge uniformly on every compact subset. They all are defined on some, it's all holomorphic on some open set containing some fixed compact set containing the unit disk, and the operator has norm most one. Then if those holomorphic sequence of holomorphic functions converge uniformly on every fixed compact set, which is contained uniformly contained in all their domains of holomorphism, then in fact, maybe I do want to have a fixed open set where they're all holomorphic, and then you look at the convergence to be uniform on any fixed compact set contained in that, containing the unit disk. Well, in that case, the functions, the elements of the Banach algebra, the elements of the complex Banach algebra, you get by plugging in the given element in your sequence of holomorphic functions according to this all the holomorphic functions calculus, which is unique with this continuity property being a polynomial. Well, the continuity property is in this setting. It converges. The elements converge. Okay, just like with the continuous functions converging in the suit norm on the subset. It doesn't have to be as large as it has to be now. So it's not enough just to be holomorphic on the. Well, it doesn't quite make sense. The spectrum is a compact set, right? A closed set. It doesn't quite make sense. It doesn't quite make sense for a function to be holomorphic on a closed set. But if it's holomorphic on an open set containing the some closed set, or for instance, the unit ball of the operator. The unit ball of the plane. The unit disk in the plane. And the operator, Banach algebra L, which has norm 1. So then you can. Then you have want to. I don't want to have to write the formula for the element on the board, okay? But you can do it. It's just the same as the Cauchy integral formula. Okay, and instead of a scalar, Cauchy integral formula, you put a scalar, right? Well, instead of the here in this present case, instead of the scalar, you put an element of the Banach algebra. But now there's even a remember for the continuous functional calculus, you could do it for the interval, going from minus the norm to plus the norm. You could also do it for the spectrum, which is smaller. So it's important here you can do it for the spectrum too. There's an open set containing the spectrum, compact set containing the spectrum. Arbitrary, so fixed open set containing the spectrum, and arbitrary compact set containing the uniqueness, continuity. In many cases, you just want to use the formula. You don't have to worry about uniqueness. You just apply the formula. You want to know the map from the functions to the element. Plugging in the element into the function. This is multiplicative. Maybe I forgot to mention that. You might take a product of two holomorphic functions and plug in each one of them, or plug in into the product. Then you get the same thing. Okay? The holomorphic. So why is that important? That's important because if the holomorphic function is just equal to 0, if the values on the open set are just 0 or 1, then it's equal to its square. Okay, but that means that if you plug the operator in, plug the Banach algebra element in, that's going to be equal to its square too. So you got your idempotent. That's how you get the p. But how many holomorphic functions are there with all values only 0 and 1? Well, yes, yeah. Well, that's if the domain of holomorphy is a simply connected open set. That's why I'm not finished yet. Okay. You can have two open sets instead. But then two open sets will not contain they won't help covering the unit disk, right? But they will help covering the spectrum. So what we want to do is show that this linear polynomial, it's the spectrum for every z, every value of z. The spectrum, we want to show that the spectrum is contained in always in two open sets, two disjoint open sets. And then we can take a holomorphic function, which is 0 here, and 1 here. And it'll be holomorphic on an open set containing the spectrum. That's how you do it. Does that make does that make sense? Okay. Well, so you see why I gave it a big spiel about the easiest thing is if you take the whole simply connected set containing the spectrum, because the self-adjoint case, the interval from minus the norm to plus the norm, and then the Banach algebra setting, you take the ball of radius the norm of the element. That's just fine if all you want to do is plug your element into some holomorphic function on the whole disk. But if it's not holomorphic on the whole disk, so what happens here? What's a good exercise? Look, what we know. By the way, we know that we know that a0 plus a1 is equal to 1, right? So what this is 1 minus a1 plus a1z. It's 1 minus a plus az. That's exactly the same as this, except instead of the p, we just have an a. And we'd like to show that the spectrum of the A, sits inside two open sets, two disjoint open sets. One of them containing 0 and one of them containing 1. Then we're indifferent. Okay. Well, that's a good exercise. Try it for complex numbers. Just take A to be a complex number, and Z to be the usual Z, complex number of absolute value 1. Suppose that this is so it's invertible, right? That's the condition. Suppose this is non-zero for any Z. Can you prove that the A must lie in two disjoint open sets? One must lie in one of two fixed universal disjoint open sets. Okay, that's it's probably too easy for it's very elementary. So it's complex. It's not complex analysis. It's complex arithmetic. Okay, high school level, someone learns about complex numbers, addition and multiplication. It has a simple answer. That's why I'm not. That's why I'm trying to hide it, make it look more mysterious. Okay, but that's how it goes. Okay. And but it's enough by working the spectrum in Banach algebra. The problem reduces to, if you want to prove the spectrum is in the union of two disjoint open sets, two universal disjoint open sets. Well, if A is an element of a Banach algebra over a complex number, then the spectrum of this element for fixed Z, the spectrum is just the set of, put lambda in the spectrum of A. And it's a set of 1 minus lambda plus lambda Z, where lambda is in the spectrum, arbitrary element in the spectrum of A. That's a special case of what's called the spectral mapping theorem. It's true for polynomials, it's actually true for holomorphic functions, and true for continuous functions in the setting we discussed. But we don't need that. We just need the true for linear polynomials. That's the mapping theorem. But that's elementary. The spectrum of polynomial, linear polynomial in a single. It's important. It's important to be a commutative Banach algebra. See, the 1 minus a and a commute. So it's pretty much commutative Banach algebra. But for something in the spectrum of this for fixed Z, it's exactly the same as it being 1 minus lambda plus lambda Z for lambda in the spectrum of A. Okay, well, that's,